So the four kinematic equations, they're also referred to as the motion equations. These are equations that you're going to be using throughout the whole year, because pretty much every topic in physics involves motion. So this is not just going to be for Chapter 2. You're going to use these in Chapter 3, Chapter 4, Chapter 5, and as you already know, we're not covering nearly as many topics as we did last year. So the other classes were asking, do you have to memorize these? Yeah, but it's not going to be difficult because you're going to use them so much. Okay, so defining the variables. The only thing I really have to point out is that x, last week I made a big deal about saying that displacement was delta x. Last week, what did we define x as? Position. X was position, like where you are in the world, and then delta x was displacement, right? Displacement also measured in meters. Now, in these equations, it's very common when you're doing the kinematic equations just to understand that x represents displacement. So technically speaking, these x's here really should be delta, like this right here, that should be delta x. I just write it as x. I think it's easier. So pretty much from here on out, when we do the motion equations, know that x is really displacement. You follow me? Change of position. All right, what would A be? A is acceleration. T represents time. How about this VF? Final velocity. And then V naught, that little zero there, that subscript zero, is they call that V naught. What does that indicate? Initial. Now sometimes in some worksheets or some textbooks, V initial is written as V sub I. You know, I'm sure at some point this year I'm going to give you a handout where initial velocity is V sub I. Sometimes velocity final is just V. Like the way some books do it, V is the final velocity, and then VI is the initial velocity. Okay? But I think it's pretty self-explanatory. So here's a sample problem. And I purposely made this real simple because I want everybody to understand it. There will be no confusion. And then after we do this example problem, I'm going to talk about two things that will make these kinematic problems more challenging. But we're starting out with a nice easy one. So first thing when you're doing a physics problem, and I mentioned this in the email, everybody got my email I sent? Yeah. So I mentioned in the email what I'm looking for in your homework sets. So what I want to see for problems that involve a situation, which is like 95% of physics problems, it's going to be like a guy does this, a guy jumps off a diving board, a guy skis down a hill, a car accelerates from rest. So what you're going to do is you're going to take the situation and you're going to draw a little picture for it, and then you're going to label all the given information onto the picture. Okay? This is what you do for the homework set. Now, what if it's like a problem where they give you a graph and then ask you a question about the graph? Do you have to like draw a picture for that? No. Or what if it's a conversion problem? 200 miles equals how many meters? You can't draw a picture for that. So, but pretty much you're always going to have a situation that can be turned into a picture. So here's a picture we have. The initial velocity is 2 meters per second. We're told that right here. The car accelerates at 3 meters per second squared, which you now know what that means. What does 3 meters per second squared mean? It means 3 meters per second every second. The car changes velocity by 3 meters per second every second. Okay, what else do we have? We have the time. The time is 4 seconds. And we don't have final velocity, but put it on the diagram anyway. Put it on the diagram and label it question mark. And then we don't have the displacement. Displacement, we're indicating that with an x rather than delta x. Okay? That's the diagram. Now, first question. Find the displacement of the car during the 4-second acceleration. So which of these equations could be used. And I should mention, sometimes 3 of the 4 will work. Other times, none will work. You know, if you come across a problem where you're like, doesn't work, doesn't work, doesn't work, doesn't work, does that mean that the problem's not solvable? Not quite, because what you do then, if none of the kinematics work, then what you do is solve for something else, solve for another unknown that you can get, and then once you get that unknown, then it kind of unlocks the problem, and you're like, oh, I got that, so now I can get this. But anyway, so which equation here will work?
First one.
The first one, and this is the only one. If you want to solve directly for displacement, the first kinematic is the only one that'll do it, because the problem you run into with the other ones is we don't have velocity final. Okay, so the way you show your work, this is when you're doing your homework format. If you want to be awesome, which you all do, I know you want to be awesome. On the AP exam, what they look for, what the grader looks for on the free response is correct equation. So the thing I've noticed over the years, kids want to go straight to the numbers. Like, don't show the equation, just start putting numbers down to figure it out. You got to get in the habit early on by showing the equation, then doing any algebra necessary to solve for what it is you're trying to get, and then lastly put the numbers in. Numbers go in last. Okay, so show the equation. We go x equals 1/2 at squared plus v initial t, and now we plug numbers in because it's already solved for x. The acceleration is 3. Show units in the work. Units in the work. Initial velocity was 2. Time is 4. So this gives us an answer of positive 32 meters. Positive meaning to the right. Oops. Positive to the right, negative to the left. Pretty straightforward. Okay, part B, find the velocity of the car after the 4-second acceleration. So to find the velocity, would this equation work? Yeah. Would this one work? Yeah. Would that one work? Yeah. So 3 of the 4 work. I think that this one looks easiest. I don't know about you. So I'd go like this. So you show the equation, show the grader. VF equals V initial plus AT. Say, hey, this is the equation that I'm using. Then plug numbers in. So velocity final equals the initial velocity, which is 2, plus acceleration, which was 3, time, which was 4. So this comes out as 14 meters per second, positive, indicating to the right. Okay? Any questions on that? So that just gives you a feel for how the kinematics work. Now, 2 examples of more challenging kinematic problems. Like what would make a kinematic problem more challenging? First one, problems that involve plus and minus. Notice that this problem here, everything was plus. Everything was like to the right. But is it possible where you have an object moving to the right, which would be plus, but accelerating to the left, which would be minus? Is it possible to have a positive velocity but a negative acceleration? Yeah? And what would be happening there? The car's slowing down, right? In fact, if I were you, I'd write in your notebook, whenever velocity and acceleration have opposite signs, the object is slowing down. Whenever velocity and acceleration have opposite signs, the object is slowing down. And whenever they have the same sign, the object is speeding up. Okay, so that's the first example. situations where you got to pay attention to plus and minus, right? Second example, situations where there's a change in the acceleration. Now, one thing to know about these kinematic equations, in order to use the kinematic equations, acceleration must remain constant. If the acceleration changes, well, then there's something you got to do. Anybody tell me? What do you do if the acceleration changes? Like from one acceleration to a new, so it'd be like this. From one constant acceleration to a new constant acceleration. Because to use the kinematics, the acceleration of the object must be constant. You can't have this like changing acceleration. So what do you do if the acceleration changes from one constant acceleration to another constant acceleration? You have to what? Not average them. You gotta, yeah, two different parts. You gotta break the problem into like part 1 and part 2. And then if the acceleration changes again, which you will have a problem like that, there's one in the homework set. If it changes again, then you break it into a third part. So you have like 3 different regions of acceleration. Well, so once you have 3 different parts, you got part 1. Like here's an example. In the homework set, there's this problem about this rocket. So this rocket gets launched from the surface of the Earth, and it accelerates upward for like 5 seconds or something. So the rocket's going like this. It's going faster, 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 faster. It's accelerating with a constant acceleration, okay? Then the problem says the engine of the rocket dies. So just imagine that. The engine just turns off. Then it becomes this dead mass, right? Now, is that rocket going to instantly fall? No, because it was going upward. So as soon as the engine dies, it's going to keep moving up. But what changed? What changed when the engine died? The acceleration changed. It went from being an upward acceleration to a downward acceleration, which would be the acceleration of gravity. So what you do when you're setting that problem up, you draw a line and you say, boom, right here is where the engine died. First part is the positive acceleration. Second part is the negative acceleration. And then what connects part 1 and part 2? Well, the final velocity of part 1 is the initial velocity for part 2. That's what connects the two. Okay? And we'll look at this. I just want to point this out. All right, so now let's move on to free fall problems. So what I want you, I'm going to give you like 2 or 3 minutes. Copy all this down into your notes, and then there's 4 things you have to know about a free fall problem, and then we're going to solve this example, and then that's it for today. So take about 2 or 3 minutes. 4 things, so these 4 things, and then I'm going to let you guys try this example problem, which is a super straightforward free fall situation. Okay, so the 4 important things. Well, I guess I should start by saying, what's the definition of free fall? And I like to talk about this because when you hear the word free fall, what you hear is fall, which makes you think down. An object could be moving up and be in free fall. Like I take this baseball that I'm holding in my hand, I throw the baseball up like this, that would be free fall, up and down. The definition for free fall, it's when the only force acting on the object is gravity. If you want to make note of that, it's when the only force acting on the object is gravity. That is free fall. And I should mention, with where we are in our study of physics, we ignore air resistance. Air resistance does not get factored in. That's a super common question that kids ask. You know, they'll say like, well, in real life, and I'm like, well, yeah, this isn't real life. This is like the world of the physics textbook. I mean, which is the world, but it's the world simplified. If we had to factor in air resistance today, you know, it'd be much more complicated. So we simplify things by saying, yeah, no air resistance, even though it's present in real life. Okay? So An object in free fall is where the only force present is gravity, like a ball flying through the air, or like you ride your bike off this gnarly jump or something. As soon as you leave the ground, you would be in free fall, okay? Because gravity is the only force on you. All right, so for an object in free fall, number one, the acceleration is equal to gravity, -10 meter per second squared. If you're doing problems in the homework book, use 9.8, so that way your answer matches up with the answer in the back of the book. But in class, like for worksheets and things, we just use 10. On the AP exam, you're going to use 10. Okay? Second thing, the velocity at the highest point is equal to 0. And if you think about it, this has to be true. You know, if you take an object and you throw it up in the air, so this object goes up, 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 there has to be a point where it stops for a split second. It's the point where the velocity changes from up to down. So it just for a fraction of a second, it stops. The velocity goes to 0. Now, will free fall problems specify these things here for you? These first two? Are they going to be specified? No. The problem's not going to mention it. It's not going to tell you, oh, by the way, the acceleration here is gravity because it's free fall. The problem is not going to tell you that the velocity at the highest point is 0, so you just have to know it and remember it. Same thing for 3 and 4. So third thing, you should know that time up equals time down, assuming that the object returns to the same level. You know, so here, you know, the ball goes up and then comes back down again. The time to right there, the time up and the time down are the same. Now, what if it didn't return to the same level? What if we looked at the situation where the ball like landed down here? Then would time up and time down be the same? No. So as long as it returns to the same level, time up and time down are equal. Lastly, which is why we don't shoot guns up in the sky. If you shoot a gun up in the air, you're like, bang, bang, bang. That bullet, let's say it leaves your gun at 200 miles an hour, assuming no air resistance, which is not really possible because in real life there's air resistance. But just for a moment, if there was no air resistance and you shot a gun up in the air and the bullet left at 200 miles an hour, how fast would that bullet come back? 200 miles an hour. Now, in real life that has air resistance, would it come back faster or slower? Slower, because the bullet got slowed by the air. Okay, but for physics problems, if an object leaves at 8 meters per second, it's going to come back at 8 meters per second because we assume no air resistance. Okay, so any questions on those 4 things? So let me give you guys 3 minutes. I'm going to erase. Everybody's got that copied in their notes? So take 3 minutes and then we'll solve this. Do is draw a diagram with all the given info. So here the ball is. It starts out with an initial velocity of positive 8 meters per second. So I'm going to put down the sign convention. We're saying that up is plus, down is minus, like that. So it starts out with a positive velocity. The ball goes up, 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 up to the maximum height, up to here. And then what do we know about the maximum height? Velocity equals 0. And notice the problem did not give that to us. And then there's one other thing we know that wasn't stated. Acceleration's gravity, which is -10 meters per second squared. Okay, we don't know time, so label that as a question mark. And then the displacement from the starting point to the ending point, we'll label this x. So from here on, we'll just say that x represents displacement, even though technically it's delta x. I'm not the only crazy one that does this. I've seen this in the books too. X represents displacement. Okay, so x is a question mark. Now, looking at the list of kinematics, so number 1, finding the maximum height the ball will reach, which is x. Oh, and look, I know somebody would In fact, I should not even mention it, and somebody's going to ask. Do any of you have a thought about this? Other classes asked about this. So finding the maximum height, like how could we really find the maximum height when we don't know how high above the ground? Like, you know, what is this distance there? We don't know. Was anybody wondering that? Nobody? Oh, other classes asked. A very common question. So for a situation like this where they say maximum height above the from where the person threw it, all we can do is calculate maximum height from the point of release. All we can figure out is maximum height from here, right? Because we don't know how tall the guy is or where his hand was. So anyhow, how do we get maximum height? Well, which kinematic would do it? There's only one. There's only one motion equation that'll work here with the information we have. The last one on the list. V final squared equals V initial squared plus 2AX. Now, show the equation first. I want to make you guys awesome. So when the grader gets your exam in May, they're like, wow, this kid is incredible. Okay, do we put numbers in yet? Because what are we solving for? X. Do the algebra first. So X is going to be VF squared minus V initial squared over 2A. That's what it simplifies to, algebraically. Then put your numbers in. So V final is 0. V initial was 8. Put units in the work, be awesome. Acceleration is negative 10. So notice here the the negative cancels, and we end up getting 3.2, what is it, 64, 20, what is this going to be? Yeah, positive 3.2 meters for maximum height. Okay, second question. The time that the ball will spend in the air. Now what I like to do for a problem like this is solve for the time up and then double it to get the total time in the air. So calculation number 2. Which equation could we use to find time up? So what I'm going to do is I'm going to solve for the time to there, up to the maximum height. I know that time up and time down are equal. So once we know time up, we can just double it. So I would use V final equals V initial plus AT, and then rearrange this for time. Time is going to be V final minus V initial over A. Using up here, using the maximum height to be the final point. Final velocity is 0 meter per second. Initial velocity is 8. Acceleration is negative 10. The negatives cancel, and we get 0.8 seconds. And then we take the 0.8 seconds, because that's only time up. Take the 0.8, multiply by 2, we get 1.6 seconds. So total time in the air, assuming it returns back to his hand, is 1.6 seconds. And then the third question, what's the velocity 1 second after being thrown? We go V final equals V initial plus AT. So V final equals, so V initial was 8 plus acceleration is negative 10 meter per second squared. Time is 1 second. So this gives us a final velocity of negative 2. And then that negative means what? On its way down. It's coming back down.